Very good morning. So last time we have seen some of the results regarding monotone sequences, and this application of the sequences can be observed in various real-world processes, like in stock market, in predicting the weather conditions, and satellite design, construction, and so on. And once you know that design or that model behaves like a Cauchy sequence, means that we are going to learn just now, or it's going to be behave like a monotonically increasing or decreasing. So you accurately you can talk about the things. Okay, right. So, for example, if you want to suppose you have a structure and you want to know how it is going to be react with respect to the weather conditions. Okay, in in coming 2 days or like a couple of decades. So if you have the historical data, and if the historical data tells you that it's behaving like a Cauchy sequence, or then you can definitely tell something about it, that okay, how it is going to be respond with respect to the weather conditions and so on. So they have the sequences are very rich in applications. So we will say that is a given sequence is a Cauchy sequence if after some stage uh, the points are sitting very close to each other. Many time in the real processes, you don't want to know where you are going to converge. Okay, the limit value you may or may not be interested in, or you may not be able to find out. So what the Cauchy criteria tells you, that for every epsilon greater than 0, so you will able to identify a stage where means afterwards that point the things are getting very close to each other, you can say, in other words. So if epsilon is very small, this points that's saying that these points are sitting very close to each other. So infinitely many points are sitting all together except the finitely many, you can say. Okay, so but those finitely many, it be means like is not, it may not be a number as 10 members or 100 members. It may be lakhs members as well. Okay, so it depends on what epsilon value you choose. Okay, so this definition tells you, so if I read it, so a sequence of real numbers is said to be a Cauchy sequence if for every epsilon there exists a natural numbers h epsilon such that for all natural numbers, you take any natural number, two natural numbers greater than equals to that h epsilon stage, you can say the terms are satisfying the following, means they are sitting in the epsilon neighborhood of it. Okay, right. So this means the terms afterwards, this epsilon, afterwards this stays at epsilon, they are sitting very close to each other. So let's try to look at some example here, and then you may be able to get more insight about it. So let's consider the following sine wave. Okay, so you can see these are I mean, it's like you can take the sequence sine of 2n plus 2n minus 1 pi by 2. Okay, so this is nothing but the minus 1 to the power n. Okay, right. So n is equals to 1 pi by 2 and 3 pi by 2. So it's oscillate. Okay, so you can, so here, if you look at the sine wave closely, so if your historical data behaves like this, so it's not falling into the Cauchy criteria. Why? Because you will not able to find any stage where the infinitely many points are sitting very close to each other. On the other hand,
Yeah.
if
For n equal to 1, sine pi by 2 equal to 1 and minus 1
yeah,
is to 1.
so think then this is minus 1 to the power n plus 1. Right? It's fine. Okay, so we can modify it, right?
Yes.
Yeah.
Yes, sir.
Okay. Okay. Right. So the sine wave behaves in a manner, okay, that if you generate a sequence over it, so it's oscillate between. So we know that this is bounded. Okay, the sequence is bounded. This lies value. All you take values. There are lies between -1 to 1, but they don't follow the Cauchy criteria. Even they are not converging anywhere, because if n is even, you are finding the value is -1. If n is odd, you are finding the value is 1. So it's oscillate. So oscillate sequences are not converging. Okay. Instead of this, if sine wave, if you follow this wave here, okay, some wave. So afterwards, you can see this wave is getting closer to each other, means like closer to this x-axis. Okay, and so this will be like, afterwards, and like you have this is means like very close to. So you will find a certain points afterwards. It's lies like y equals to 0. Okay, so this wave is getting the in the shape of Cauchy criteria. That's what we can say. But we don't know where does the limit goes. Okay, so so it is very clear that Cauchy criteria will not tell you that what is going to be the limit, but what it will tell you is it has the behavior of a very special type of sequence. Okay, and you will see that in a real field, okay, in a set of real numbers, which is we are known as real field, that every Cauchy sequence is convergent and convergent sequence are Cauchy. So these are if and only criteria. Okay, so once you have in the real field certain sequence is Cauchy, you can certainly tell about that the sequence converges. If sequence converges, then it is Cauchy. These are if and only. It's either you look at this side or that side. Both are the same thing. But one side will give you the limit value, and other side will not tell you the limit value, but only tell you the behavior of the sequence. Okay, right. So let's take some example. So the sequence 1 by n is a Cauchy sequence. We have already seen that the sequence is convergent. Okay, and converges to 0. Okay, now if you want to show that sequence is Cauchy, yes, like so this is here xm is equals to 1 by n. So let epsilon greater than 0 be given. Okay, so let epsilon greater than 0 be given. Okay, now since this sequence is convergent, okay, since this sequence is convergent, okay, we know that limit of 1 by n is 0. So we know that, so there exists a space k epsilon belongs to n such that 1 by n is less than epsilon for all n greater than equals to k epsilon. So can we utilize this fact? So, okay, to prove that this is a Cauchy sequence. So this can be proven by using Archimedean property, or you can use the fact that this sequence converges and converges to the 0 value. Okay, so now similarly, so if you take any, so this implies 1 by m also less than epsilon for every m greater than equals to k epsilon. Right, because this is true, this result holds true for every m greater than equals to k epsilon. So if you take any m also greater than equals to k epsilon, that also follows this. Now what you will want to look for is I want to look for the difference mod of xn minus xn. So I take this xn minus xn, that is going to be 1 by n minus 1 by m, and use the triangle inequality. This is less than 1 by n plus 1 by n, which is certainly less than epsilon plus epsilon, that is 2 epsilon. And this is certainly because whenever for all n comma m is greater than equals to k epsilon. So that h epsilon, which you have in the definition of Cauchy, that you can you are having as k epsilon here. Okay, and note that we don't have any relation between n and m. Okay, so far. We are not specifying and maybe n is greater than m or m is greater than n. Okay, it doesn't matter. Now, if you are very specific to get here epsilon only, so replace here epsilon by 2, then you will get the epsilon plus epsilon, means epsilon by 2 plus epsilon is epsilon by 2, epsilon by 2, 2 times is give you epsilon. Okay, so if you are very specific to epsilon, to getting, means to match with the definition. Okay, or else you can also say that there's that 2 epsilon. See, it's constant multiplication of epsilon will not cause any issue. Okay, only issue will come if you have epsilon multiplied by some function of n, or here means 1 by n or 1 by m type. Okay, which is not fixed. Okay, which is varying. Okay, so keep that you can note that. Okay, so if you are getting in somewhere, some people will start and then will start like they are getting 3 epsilon or 4 epsilon or 5 epsilon or epsilon by 4. Okay, the constant multiple of epsilon will work because you have the chance to go back and modify your epsilon. Okay, so that will not make any difference if you have less than 2 epsilon or 4 epsilon or 5 epsilon here onwards. Okay, right. So let's take one more example. Okay, and that we have already seen. Okay, so that we have already seen that the sequence 1 plus minus 1 to the power n is not Cauchy. So what if you want to show that certain sequence is not Cauchy? Okay, because you have this sequence is behavior like if you have n equals to 1. So you have n equals to 1 means 1 minus 1, that is 0. Okay, if you have n equals to 2, so you have 1 plus 1 is 2. So you have this sequence like behave like 0, 2, 0, 2, 0, 2, and so on. For this particular sequence, this is the type of the sequence it is. Okay, now we want to show that see we can certainly see the behavior of the sequence that at the large value of n, we don't know whether it is 0 or 2, because large value of n may be even number, maybe odd number, we don't know. Okay, so in the limiting sense, it will not converge, in other words. Okay, or also not means also that they are not getting closer to each other. So what is the negation of the Cauchy? Means if you are able to identify an epsilon naught, okay, or fixed epsilon. So because if you are able to identify epsilon naught greater than 0, such that for any h means h epsilon such that afterwards they are means like xn minus xm is greater than equals to epsilon naught for all n comma m greater than equals to h epsilon naught, means they are going very far or equals to epsilon naught. Okay, so this is what it the negation of the h epsilon, because you are able to so for given epsilon you are able to identify and stage such that that mod of xn minus xm is less than epsilon. So if you try to look at the negation of it, so you try to get an epsilon naught such that you take any value of h epsilon naught. Okay, means h epsilon naught is a natural number. For any h epsilon naught, mod of so they are sitting greater than equals to epsilon naught for any value of n comma m. Okay, so in this case, what the epsilon naught you can give is, you can see the distance is 0 to 2. Okay, so you can take the midpoint as well. Epsilon naught is you can say 2 1. You can also give epsilon naught equals to 1. Okay, and you take any, so for any n you belongs to natural number. Okay, so let's say for any h belongs to natural number now. Okay, mod of xn minus xn plus 1 or xn minus 1. if you choose m is n minus 1, you can fix this m as well. That is going to be 2, which is certainly greater than 1 for any n, whenever having, for any n greater than h. Okay, so this tells you, so epsilon naught means you cannot, means you may not take 1, you may take 1.5, you take, okay, so if you take epsilon naught greater than 2, it will not work. Okay, because 2 is not greater than, it means like greater than 3 or greater than 4. Okay, you can choose any value between 0 to 2 interval by looking at this sequence here. Okay, right. Now, what is important here is now is if X is a convergent sequence, then X is a Cauchy. Okay, so this result is immediate, so we can have the proof of it. So if a sequence is given and if you know that it is a convergent sequence, then it is Cauchy. Okay, so the converse, if you try to find out what is the converse, is if X is Cauchy, then whether the sequence is convergent or not. Okay, but in real number, yes, okay, they are if and only if. But if you go for another spaces, okay, so it may not be true. Okay, so if X is a convergent sequence of real numbers, then X is a Cauchy sequence. It has very simple proof, like we have done approach to identify that the sequence is a Cauchy sequence. We are going to proceed in the similar manner here. So, if you are going to look at the proof of this result here, so it is given that it's convergent. So let's say limit of xn is equals to x. Okay, we want to show that x is a Cauchy sequence. So let epsilon greater than 0 be given. So then there exists a stage k epsilon such that mod of xn minus x is less than epsilon for all n greater than equals to k epsilon. Now, can we utilize this fact? Now, mod of xn minus xm, I add and subtract here at x. Okay, so this is equals to mod of xn minus x plus x minus xm, and then we will use the triangle inequality. Okay, so this is going to be, if you use the triangle inequality, so this is this further less than equals to mod of xn minus x plus mod of xm minus x, xm minus x. So what we have is mod of xn minus xm is less than equals to this because of triangle inequality. Okay, now we know that this modulus value is less than epsilon whenever n is greater than equals to k epsilon. Similarly, we can also apply this whenever m is also greater than equals to k epsilon, that also will remains true. So this is going to be less than epsilon plus epsilon for all n comma m greater than equals to k epsilon. So the same k epsilon will work. So which is 2 epsilon here. So as I mentioned already, you can go back and you have a chance now. So you can go back and modify your epsilon by 2, and then you can match with the definition. Or else the constant multiple of epsilon is we are least bother about it. We are not bothered much about it. Okay, so this tells you, this implies, so you have started with an epsilon greater than 0 and you are ending with this. So this tells you that sequence xn is Cauchy. Not only that, okay, what other property Cauchy sequence has? So if a sequence is convergent, you have known that this is bounded. Okay. Okay. Now we want to show that if a sequence is Cauchy, then it is bounded. So if I want to claim that every Cauchy sequence of real numbers, or every Cauchy sequence is about it just now. Every Cauchy sequence is bounded. So we are talking about real number case, so it's well understood that we are talking about Cauchy sequence in set of real numbers. But this result holds true for other spaces as well. So every Cauchy sequence is bounded. So how do we claim it? So let Xn be Cauchy. Okay. Now fix epsilon by epsilon not greater than 0. Then you will be able to find there exists an epsilon naught natural number such that mod of xn minus xn is less than epsilon naught for n, comma m greater than equals to this h epsilon naught. Right? So now this implies mod of xn is equals to mod of, so I'm going to use this fact now, so mod of xn minus x h epsilon naught, this is plus h as h epsilon naught, uh, x h epsilon naught. So use that triangle inequality now. This is going to be less than equals to mod of xn minus x h as h epsilon naught plus mod of x h epsilon naught. So h epsilon naught is a natural number. Okay, thus you can make it more simple notation. Okay, here. Now see, this is going to be less than epsilon naught whenever n is greater than equals to h epsilon naught, and this is a fixed number, right? Fixed number. So this is going to be less than epsilon naught plus mod of x h epsilon naught. So we are proceeding in the same way what we have done for the convergent sequences. Okay, so what it tells you is, so this result implies mod xn is less than epsilon naught plus mod of x h epsilon naught for all n greater than equals to h epsilon naught. So this is a fixed number, so you choose, so choose m is equals to mod of x1, mod of x2, and so on, mod of x h epsilon naught minus 1. Because after n greater than equals to h epsilon naught, it is bounded by this number. So, and with epsilon naught plus mod of h epsilon naught. You choose this m. So then mod of xn is less than equals to m for all n greater than equals to 1 for any n now. Okay, right. So this tells you that every Cauchy sequence is bounded. But just now you have seen that if a sequence is bounded, it may or may not converge. Okay, so that you can look at the minus 1 to the power n, or we have seen the sequence which is not Cauchy, but it is remain bounded because it is oscillating between 0 and 2. Okay, right. So every Cauchy sequence is bounded. Every convergent sequence is Cauchy, is in the okay. These results holds true for any spaces. But what about the converse is that Cauchy which is known as Cauchy convergence criteria. So a sequence of real numbers is convergent if and only if it is a Cauchy sequence. Means if a sequence you are identifying that it is a Cauchy, it converges. If a sequence you are identifying that if that sequence is convergent, then you can certainly tell that it's a Cauchy. So these are if and only if. Okay, the proof we are not going for means inverse here. Okay, that we are because we have not talked about the this subsequences and so on. So it uses the famous result known as Bolzano Ristrauss theorem, which says that every bounded sequence has a convergent subsequence. So we are not get into detail now. Okay, so but we are going to use this result as it is. So if you talking about in the case of real numbers, so this note that this sequence, this convergence criteria is hold true for real numbers, real in the set of real numbers. Okay, this convergence criteria will be generalized to the spaces, and then you will say this is complete if and all. So these are things we are just omitting these details here because this is beyond the scope of this course. Okay, so we are only in real numbers, so this Cauchy convergence criteria holds good for the case of real numbers. Okay, right. So this is these are the interesting properties of Cauchy criteria. Okay, right. Now we have, so see, we have seen that that when your sequence is converges to certain limit. Okay, so sometime you have the sequence which you will not decide, like oscillating sequence 0 2, like we have seen. Okay, previously 0 comma 2 0 comma 2 and so on. This is bounded. This is not going to plus infinity, right, as last value, and it is neither going to towards minus infinity. Okay, so we also try to identify the definition, what would be the possible proper divergent sequences, means they are tending to plus infinity or tending to minus infinity. That also have some good applications. Okay, so let xn be a sequence of real numbers. So how do you this results are looks like very messy here. Okay, so but if you want to understand, okay, when you will say that certain sequence is tending to plus infinity or tending to minus infinity, so let's understand by geometrically first, and then we will come back here. Okay, now you have the a real line. Okay, you have the real line, and you have the sequence x1, x2, x3, and so on. Maybe sitting somewhere, means here, here, here. Okay, they can be enumerated in order as well. Okay, so let's say this is x1, x2, x3, x4, and so on. Then when you will say this sequence is going towards plus infinity, means it is not converges. So where what will happen with this? So it diverges properly to the plus infinity or properly towards minus infinity. So let's talk about when you will say this is going towards plus infinity. Suppose, means you take any member, okay, any real number, some number like say alpha. I'm just going with the notation which we are using. So alpha on set on the real line. Okay, alpha is any real number on the real line. Okay, if you take this, so instead of epsilon, we were working about the epsilon, right, previously. Now we are talking about any alpha. So it may be greater than 0, it may be less than 0, or it may be 0. Okay, so it is sitting on the real line anywhere. So you take any alpha, then you are able to identify a stage, so that afterwards all the infinitely many terms are lying on the right of it. Then you will say that diverges to plus infinity. You fix any alpha. Okay, means you talk about any alpha. For example, let's talk about the set of natural numbers. Okay, so set of natural numbers. So let's say this is 1, 2, 3, 4, 5, 6, and so on. These natural numbers can be identified on real line. This is somewhere, this is, let's say, 0, 0 point. Okay, right. So these are natural numbers on the real line, which is this sequence is n. Okay, now if you look at the behavior at large value, it's tending to plus infinity. That's now if you fix any alpha, any point alpha anywhere. So let's say this is alpha. Okay, then after n equals to 2, greater than equals to 3, So all the members are sitting on the right of it. You may take here as well. So there it may be natural number. So you know that every real number y greater than 0 lies between two consecutive natural numbers, right? Ny minus 1 less than equals to y less than equals to ny. If you recall from the Archimedean property. Okay. So this, suppose you have taken this, let's say this is alpha 1. You can take this as alpha 2. Okay. Now you will definitely able to identify a natural number which you can say this is n and this is n plus 1. You will able to, it will be sitting between two consecutive numbers. Okay, then afterwards, whatever the n plus 1, n plus 2, n plus 3, and so on, they are sitting infinitely many. So till only finitely many on the sitting on the left. Afterwards, all the infinitely many members of the set of natural numbers are sitting on the right of it. So you can move towards the plus infinity. You can point out any of the real number, and afterwards you will see that every number, infinitely many numbers are sitting on the right of it. So this sequence, we can say that this is diverging and diverges to plus infinity. Okay. Now, if you want to look for tending to minus infinity, okay, so in the similar manner, you can look at. So instead of sitting on the left, right, infinite many, then you can start talking about if they are sitting on the right, on the left of it. Okay. So if I have here, so if I have, this is, let's say, you can take a set of negative integers. Okay. So like, okay. So if you identify an alpha, oh, sorry, not, we cannot, we are not going to use the same notation. Let's say beta in real number. Okay. You can identify on the real line. And suppose your sequence is behaving such that this beta is arbitrarily chosen. Okay. Not that after some stays, let's say k epsilon, the other members are sitting, infinitely many members are sitting on the left of it. Means this is applicable for any beta. You can, this beta can be moving on in the direction of the minus infinity, or it can be here. Okay, right. So it may not be, means, see, some of the values may be positive. Okay, some of the values may be positive, but afterwards they may behave like negatively. Okay, that also can happen in the real processes. Means like certainly benefits are coming, profits is coming, and certainly the fall. Okay, so that such sequence will diverges to minus infinity. So you can talk about limit of minus n now. That is going to be minus infinity. Okay, so now let's come back to our definition, and let's see. The same way. So we say that xn tends to plus infinity, and we write limit xn equals to plus infinity if for every alpha on the real line you fix, okay, for every alpha, the alpha is arbitrarily chosen, then you will able to identify a stage k alpha such that afterwards all the terms are sitting on the right of it. Then it is tending to plus infinity. If all the terms, if you are for the similar definition, if you are able to identify a stage, afterwards all the terms sitting on the left of it, infinitely many, then it is going to be diverging to the minus infinity. So this is what
Sir,
yes,
can you please repeat
which one?
first one?
This first one.
Yes.
Okay, so let's so did you understand the geometrical approach? It's like we have tried to identify on the real line what it does mean.
Yes, sir.
So you take, so what it says is if you have been given with a sequence, okay, and suppose you have an insight that it is tending to plus infinity. Okay, how do you means go with that is to take any alpha on the real line, any number, any real number on the real line. Okay, then if you are able to identify a stage, so stage is identified by a stage like xk alpha, means like after xk alpha, or you can say a stage means after k alpha steps, you can say 1, 2, 3, 4, and so on, k alpha steps. then all the terms are sitting on the right of the alpha. Okay, then you will say that this diverges to plus infinity. So alpha could be how large also. You can take alpha as 10 million. Okay, or you can say, oh, okay, and alpha could be 10, alpha could be 100, alpha could be any number, large number as well. Okay, so you are able to identify infinitely many terms are sitting on the right of it, then it is tending to the plus infinity. Okay, right. See, look at, so if you identify the xn greater than alpha means they are sitting on the right of it. And this alpha now, if you vary, so this alpha you can stretch this as well. Still you are able to find a stage where they are sitting on the right of it infinitely many. Only finitely many are allowed on the left. For example, this is, we have given limit of n is plus infinity. Okay, because from, you see, like alpha 2, before alpha 2, n natural numbers are sitting. Afterwards, n plus 1 onwards, they are sitting on the right of it. Now, similarly, you can identify instead of alpha 2, you have alpha 3. So it may be some m plus 1, a bit lies between m and m plus 1. Then m plus 1 onwards, so till m natural numbers, they are sitting on the left only. So finitely many. But afterwards, infinitely many are sitting on the right of. So this is how this properly divergent sequence behaves. Okay. Similarly, you can divergent series. Okay. So we say that xn tends to minus infinity when if you take any real line, and if you are able to identify a stage such that infinitely many terms are lying, means like only finitely many terms are lying on the right of beta. Okay, and infinitely many terms are lying on the left of it. Okay, so in the case, so this, when this satisfies, then we say that limit of xn is minus. Okay, now we say that xn is properly divergent. Means properly divergent means either it is 10 or minus infinity. We will say that it is a properly divergent sequence. So we have seen one or two examples. Set of natural numbers will tend to infinity by this definition. You can certainly write that now. And set of negative integers is tending to the minus infinity.
Sir,
Okay. Yeah.
can we say that in epsilon neighborhood of limit there are infinite points of that sequence?
No, epsilon neighborhood. If you take, see, neighborhood means
I wanted to add this, that if in the that limit x tends to minus infinity, if beta is sitting on the right side of the limit point, then uh, means on left side of beta there would be limit point of that sequence, and in we know that in epsilon neighborhood of limit
no. See,
we have
one
many
thing.
points.
Okay. See, if you're talking about the limit, okay, the limit is limit when the sequence is convergent. Okay, what will be the limit? Then you can start talking about the limits. Now, suppose means like sometime like advanced, if you talk about advanced extended real number system. So set of real line with set of real numbers. You know that is can be represented by the open interval minus infinity to plus infinity. Okay, we don't. These are the symbols used for large numbers on the negative side. Then, if you talk about the extended real number, so that is going to be means you are making it close. Your union this means you are making it the close number. Now, as I got from your point that you are talking about still, suppose you are saying that limit plus infinity or limit is minus infinity, then you are talking about okay, this symbol you are using as the limits now. Okay, because whenever the sequence is not convergent, we can't talk about the limit because we are talking about only finite with the set of real numbers. We are not talking about this extended real number system. That's very first thing. Okay, if you are talking about extended real number system, then certainly you can talk about this is the limit and minus infinity is the limit now. Okay, now what is your point is you take epsilon neighborhood of any limit, then you are saying that infinitely many members are sitting on the in the neighborhood of that limit. But that limit is plus infinity. So plus infinity neighborhood you can't identify. So means what we have learned in the original definition. So it requires a new definition that plus infinity neighborhood it can be given in. Okay, plus infinity neighborhood means you are able to identify a stage afterwards. This happens, something has happened. Okay, so uh, means like answering this is left of or right of the limit. Okay, so that is certainly allowed, right? If you talk about the convergent sequence, so in the convergent sequence, what was happening is you suppose your x is the limit and you take any neighborhood of x. Okay, so there we have not mentioned that every infinitely members are sitting on the left of x. So there may be members sitting on the right also. Okay, so with your point, this is going to be plus infinity then or minus infinity. Okay, so we don't want to mix it up. Did you get the point?
Yes, sir.
Okay, because in convergent sequence we are we are attacking with the full neighborhood, means like we are not saying left of it or right of it. Okay, so there may be members they are close to x that we have observed from the definition. So some members are sitting on the left of it and some members are sitting on the right of it. We can't ignore the right values as well. Because if you talk about like 1.4142, if I go back and you have the previous number is 1.414115 or 6. And here is the number 1.4143. So these are also close. This is also close to this number. So this is sitting on the right. This is sitting on the left. Okay, but so if the better approximation, this you're going to round off to this. Okay, and this is certainly cannot be round off to this, right? So what we can do is from here we can correct it in the 3 decimal place. We have 1.414. We can go with one more steps to approximate what we are going to in the real process. Okay, so limit, if you have the limit, if certain members maybe sit on the right, certain members maybe sit on the left. So that will not cause any issue. Okay, so that we are not looking to it. So whenever we are talking about the divergent sequence, they certainly don't have any limit. Okay, but we are talking about properly divergent sequence means they are diverging either positive side or negative side. So if positive side it is diverging to plus infinity. If it is diverging on the negative side, it is diverging to the minus infinity. Okay, now how do you?
What about the sequences which would diverge in both sides for integers, which would start from minus infinity to plus infinity?
So set of
We
integers.
can't find out limit. Likewise.
See, set of yes. We cannot find out the limit. That's an oscillate sequence, right? We can't say this is oscillate.
So then about 0 and 2, we have seen that it was not Cauchy. Then
Yes.
what? That was divergent. 0, 2, 0, 2,
That
0, 2.
see, this is divergent. These are divergent series. Okay, so these are divergent sequence, but we can't say these are properly divergent. Means if you are certain to say that it is going towards plus side only, or means like positive direction only, or it is going towards negative direction only, the limiting is as large value of n. Okay, then you can certainly say this is a properly divergent. We are talking about properly divergent, not divergent.
Okay.
Okay.
Sir,
Okay.
Yeah.
So when we are able to make a comment that is properly divergent sequence, if you are able to judge from the sequence itself that it is going towards as n goes to infinity, this is going to the positive direction. Means some of the values may be starting with the negative values. Okay, maybe at the starting stage you are getting the negative errors and so on. Then you start with getting the positive errors and so on. Okay, then error is increasing monotonically, you can say. Okay, so similarly here as well. Okay, so it's proper. Okay, it's not saying oscillates. Okay, right. Okay, now what more we can do with the sequence is, now we can write the definition of infinite series now. Okay, so infinite series is summation of xk. Okay, so if you sequence, if you have been given with a sequence, you can always able to write a series from it, that is known as the series, infinite series generated by the given sequence. So that we are going to now look into. Okay. So when we will say a certain sequence means certain series is generated by X. Okay, so let me first tell you how will we write the infinite series by looking at the sequence. So here, let's say we have the sequence x equals to xn. And infinite series means we want to write at the end n equals to 1 to infinity xn. Okay, we want to write down the sum of this series, means like you take extract every member and then put that down the sum, and then you will want to look at that whether this sum is finite or infinite, or you can say that the convergent or divergent. So now let's take the first term, and which we will call as S1, that is x1. Now the next term S2, you take first member and second member x1 plus x2. Now take S3 is equals to x1 plus x2 plus x3. See, this sequence is nothing but, if I want to write in the symbolic form, that's nothing but the limit of n tends to infinity, or okay, summation k is equals to 1 to n xk. Then you will certainly see. So if you go in this pattern, if we go in this pattern, so what will be the Sn or Sk, whatever. So x1 plus x2 plus x3 and so on plus xn. Means we are taking the first n term and take the sum. Okay, it is always possible to give the sum of the finite numbers, sum of the finitely many elements, you can say. But when you are talking about the infinitely many elements, it is not, it's an approximation. You have to certainly trunk out some value of n. It means you have to certainly truncate this series if you want to use it in the computer, because computer will not understand what is the infinity. Okay, so certainly you have to fix some large value as per your desired accuracy of some problem. Okay, that we are going to maybe look in the little later. Okay, now so in this way you will go. So that if you go with the so S1, S2, S3, S4 and so on, this is giving you new sequence. Okay, this is also this known as nth partial sum. Nth partial sum of this infinite series, you have summation n equals to 1 to infinity x. Now, so if you have n tends to infinity, so what you observe it, this definitely tends to this. Okay, this you can write as limit n tends to infinity Sn. Now, the definition of the convergence of this series is lies on this fact that whether the limit of this sum of n means nth partial sum is exists, okay, or this sum will converge or diverge. Okay, so you have generated a new sequence which is given by S1, S2, S3, S4 and so on. Okay, whose, or in other words, you have the infinite series whose nth partial sum is given by this. So if you are able to identify that limit of Sn, okay, limit of Sn exists means this converges. Then you will say that exist and let S is equals to limit of this Sn. Okay, it exists, and let's say we are able to identify that S, what is the limit value. Then what we will say is this infinite sum is going to be is equals to this S, that's the limit value. Okay, so this number, okay, this number is going to be the limit of this nth partial sum. It's not like you are going to put the adding infinitely many terms and see, you don't know where to add. So how would you perform the sum here? Okay, so you can talk about only in the limiting sense. Okay, so this sequence or this series we call as this series is generated by the sequence x equals to x. Okay, now so this is so we are going to take one example. Okay, just let's go with the definition first. If x equals to xn is a sequence in R, then the infinite series or simply the series generated by x is the sequence s equals to sk. What we have defined previously, it is written in the same way. S1 equals to x1, S2 equals to x1 plus x2, S3 equals to x1 plus x2 plus x3, and so on. Okay, so if limit s exists, we say that this series is convergent and denote this limit by summation k equals to 1 to infinity x. Okay, right. Now, let's see, and this xk is called, so in this series, this xk is called the term of the series, and this sk are called the partial sum of this infinite series. Okay, so these are the notations, okay, used for the terms xk and sk. Okay, right. Now we have the following series. Okay, and so we have the following sequences. With this sequence, we need to generate the infinite series, and then we will talk about the convergence or divergence. So all the results will be applicable here now. Okay, all the results will be applicable here now, what you have learned previously for the sequence, because infinite series is also now turns out to be limit of some certain other sequence. So you can apply if it's the sequence is monotonically convergent, monotonically increasing or decreasing, and comparison test, what you have learned so far. Okay, those things also algebra of limits, those things also can be also applied here in this case. Okay, so let's look at these examples explicitly now. So if I talk about the first example now, the given sequence is x equals to r to the power n. Okay, now so then you have sk. I'm directly writing sk is nothing but r plus r square plus r cube plus and so on r to the power k. Okay, now what we want to see whether this so infinite series, let's write out what will be the infinite series here is summation. So we want to write the infinite series generated by the following sequences of real numbers. Okay, so you have, this is sk, so k is equals to here 1, 2, 3, 4, and so on. Okay, then limit of sk, or you can say sn, instead of k you can use n also, is going to be summation k is equals to 1 to infinity r to the power k. So we want to show that when it will converge and when it will diverge. Okay, so this will be the series like r plus r square plus r cube plus and so on. So 3 dot in mathematics means it's continued. Okay, so if you use 3 dots in mathematical notation, it is says that it's continued to further. Okay, right. So this is the infinite series generated by the given sequence. Now we want to see that whether this converges or not. Suppose let limit of Sn is equals to S. So instead of using this, okay, so let's use the fact that Sk is equals to R plus R square plus this one. Okay, so we instead of this, we are going to use the fact that, okay, so it is given that S, so we have the generated series whose nth partial sum is going to be R plus R square plus R cube plus and so on plus R to the power k. Now what you will do is, so multiply it by R. So it's a finitely many terms here. Okay, so finitely many terms. So you can multiply by R times Sk is equals to R square plus R cube plus and so on plus R to the power k plus R to the power k plus 1. Now subtract it. So what you will get is, so these all the terms will get cancelled, and what you will remain is 1 minus R times Sk is equals to, so this R square will get cancelled, RQ will get cancelled, and so on, RQ will get cancelled. You have R minus R to the power k plus 1. So this will imply Sk is equals to R times 1 minus R to the power k divided by 1 minus R. See, we try to simplify this because we can't work like this, okay, straightforward. So we want to use the algebra of limit and so on. So many things are already stated with respect to the sequence. So we try to write in the simple form. Means like you can also, what you can do is you can also take R from here outside, right? 1 plus R square, then you can use the fact that this 1 minus Rk by 1 minus R will be given by this. Okay, so that also you can use. Now, what we will do from this case here. So now what will happen is, so this will imply, so what we have got is, for the given sequence, Sk is equals to R by 1 minus R minus R to the power k by 1 minus R. Right? That we have previous result. Now you take this inside and you yes, R to the power k plus 1. Now this certainly implies Sk minus R by 1 minus R is equals to minus R to the power k plus 1 by 1 minus R. Now this implies mod of Sk minus R divided by 1 minus R is equals to R to the power k plus 1 divided by 1 minus R with magnitude. Okay, right. So this is going to be mod of R to the power k plus 1 divided by mod of 1 minus R. So 1 minus R is a constant. R is fixed. Now the right side, this right side will tends to 0 if mod R is less than 1. Right? If mod R is less than 1, then it will converge. Right? And tends to 0. Right? Sk minus mod of Sk minus R by 1 minus R will tends to 0 if mod R is less than 1. What about if mod R is greater than 1? Or we can say equals to 1. If R equals to 1, what will happen?
R equals to 1 undefined.
Not defined. Okay, so it will be mod R. So for R equals to 1, you can talk about separately. Because you can't talk about this 1 upon 1 minus 0, that is 1 upon 1 upon 1 minus 1, that is 1 upon 0 and infinity minus infinity. That is not defined. Okay, so you can't talk about this for r equals to 1 case. So r equals to 1 case need to be handled separately. So when you have r equals is s1 equals to, so case I just want to state uh, for r is equals to 1. So s1 is equals to 1, s2 equals to x1 plus x2. So x1 and x2 all are constant sequence, that is equals to 1 only. So s2 equals to 2, s3 equals to 3, s4 equals to 4, means one more adding, right? 1 plus 1 plus 1, right? And so on. So what will be the sk? Sk is k. K is a natural number, and you have properly diverges to plus infinity. Okay, so for the case r equals to 1, you can discuss separately. Now, for the case r is less than 1 and r is greater than 1, that you can locate here. So when r is greater than 1, this diverges. Right, this tends to plus infinity as k tends to infinity. Right? So this series tends to 0 if mod r is so that this series you have already learned previous, means that this is a geometric series. If I write it in the infinite series form, that is summation r to the power k is equals to 1 to infinity, that is nothing but r plus r square plus r cube plus r. Is the first term is geometric infinite. First term r comma ratio is r, and you know what will be sum is r upon first term divided by 1 minus r. Okay, so that here that already is during your in classes as well. I hope so. Okay, now we have one more example. Let's say that's the second part, that is x equals 2 minus 1 to the power n. And if you look at the, we are going to write the infinite series generated by this. So s1 is equals to x1, that is minus 1. s2 is equals to x1 plus x2. Okay, that is equals to minus 1 plus 1, that is 0. Now s3 is equals to x1 plus x2 plus x3. S2 x1 plus x2 is s2 plus x3, that is minus 1. s4 is equals to s3 plus x4, that is going to be 0, and so on. So what you obtain is, you have obtained a sequence of Sn. Okay, so which is such that S of Sn is equals to minus 1 if n is odd, and 0 if even. So this is oscillate. Okay, it's oscillating converts. So which is does not converge. At large value, you don't know what is it, whether n is odd or even, in the words, which does not converge. Infinite series
Yes,
also
sir.
does not. Yes, sir. Yes.
But can we say here that it is bounded between minus 1 to 0?
Yes. Yes.
And
Yes.
so 0 is a supremum and minus 1 is infimum. Can we say like that?
Yes.
Because there is only one upper bound and one lower bound.
Bound, and which is a part of the set. You can use that.
Yeah.
Part. Okay. You can
Okay,
use
sir.
that set. It is a part of the set.
Set, yes.
Okay. Okay. Then you can certainly say that this is going to be the infimum. Okay. If it is if it is a part of the set, then
Part
it is
of the set.
certainly clear. Then the last example is x equals to 1 by n into n plus 1. The sequence. Okay. So if you look at S1, what is that? Is x1, that is equals to 1 by 1 into 1 plus 1, that is 1 by 2. Or 1.1 into 2. This point is not point decimal, it's going to be 1 into 2. Now, what about S2? That is going to be x1 plus x2. That is going to be 1 upon 1 into 2 plus 1 upon 2 into 3. Right? And so on. Now, similarly, you have and so on, that is going to be Sk is going to be x1 plus x2 plus and so on plus xk. Now, each term, so you have 1 by 1 into 2 plus 1 upon 2 into 3 plus and so on plus 1 upon k into k plus 1. Now, use the fact now. So what we will use the fact that 1 upon n into n plus 1, you can write as follows. So 1 by n into n plus 1, you can write as 1 upon n minus 1 upon n plus 1. So if you use this fact, then look at S1, that is 1 by 2. What is S2? That is going to be x1 plus x2, and that is 1 by 2. X1 is 1 by 2 plus 1 by 1 by 2 into 3. That is going to be 1 by 2 minus 1 by 3. Right? So that is equals to 1 minus 1 by 3. Right? Now S3 is equals to S2 plus x3. So that is 1 minus 1 by 3 S2, and x3 is plus 1 by 3 into 4. So that you can write as 1 by 3 minus 1 by 4. So 1 by 3 will get cancelled. What you will get is 1 minus 1 by 4. Similarly, you can show that S4 is equals to 1 minus 1 by 5 and so on. So what will be Sn or Sk is going to be 1 minus 1 upon k plus 1. If you see the pattern, 2 here, 3, 3 here, 4, 4 here, 5. And you know that limit of this is 1. Okay, because this is sum of two or sum of difference of two convergent sequences. So the first sequence is constant sequence, which you can observe that the constant sequence converges and it converges to the 1. Another sequence is 1 by k plus 1 is also converges and converges towards 0. So you can use the algebra of limits here, and then okay, so since limit of the constant sequence 1 is 1 and limit of 1 by k plus 1, that sequence is 0. So this implies, this certainly together implies limit of Sk is equals to 1. And hence you have the result that what you have, the result, final result is that this implies limit of Sk, that is 1, that is equals to summation k is equals to 1 to infinity 1 upon n into n plus 1. Okay, right, sorry, k into k plus 1, because we are using index as k. Okay, right. So so this so one, you can see this one real number can be represented as a summation of infinite series. Okay, and it looks sometimes funny as well. Okay, right. Okay, so the final comment is, if the final comment is here is, if this infinite series suppose converges xk, k is equals to 1 to infinity converges. In other words, this limit of Sk exists. That's in other words. If Sk converges, then the limit of the, you can say, kth member, okay, kth term, limit of xk is 0. Not the sequence, okay, not the sequence. Okay, so, right? So if the summation xk this converges, infinite series converges, then its kth term is going to be kth term, not and kth partial sum. Okay, so kth term is going to be 0. Okay, so that can be shown very simple way. Okay, you have, this is let's say Sn is summation k is equals to 1 to n xk, right? And let's say Sn plus 1 is equals to what? Sn plus xk, sorry, Sn plus xn plus 1. Now, this implies xn plus 1 is equals to Sn plus 1 minus Sn. Right? Now, since this converges, this sequence converges, and this sequence also converges. Okay, this converges to the S, this also converges to the S. So the their difference will also converge, and that converges to S minus S, that is equals to 0. S n tends to infinity. If you are particular about n only, so you start with Sn minus 1 here, and here Sn, and then you will get limit of xn is 0. Okay, so this gives you the necessary condition, you can say. Okay, if the summation xk converges, then this limit of xk is 0, but the converse may or may not true. You can talk about harmonic series here. So if I give you that the fact that limit of xk 0 does not that the series, this infinite series converges, so you can have the counter example that summation 1 by n equals to 1 to infinity. That is that we have seen that 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 and so on. That we have seen this series does not converge. This is a harmonic series. It's also known as harmonic series. This does not converge. Okay, and but limit of 1 by n is 0. Okay, limit of 1 by n is 0. So the converse may or may not hold true. So if you, on the other hand, if you show that the given series is there, and suppose we are able to show that the limiting value of the kth term or nth term does not tends to 0, then you can certainly claim that this diverges. Okay, right. So you can use the fact that for proving the fact that the given series is divergent. Okay, for example, you have already taken the this harmonic series here. Okay, right. Or another example you can take is let's say summation 2 to the power n equals to 1 to infinity. I want to say that this series whether converges or diverges. Now note that as n tends to infinity, 2 to the power n does not tend to 0. That's it. That will claim that this series diverges. Right? As n tends to infinity, 2 to the power n does not tend to 0. Okay. So the infinite series generated by this sequence diverges. So you can use the necessary condition to discard the fact that that is going to be the given series is diverging. Okay. Right. So we are ending here now. Okay. And if you have any question, you can ask.
Sir, could you share the tutorial answer?
Tutorial answers can be shared by your TAs. They know they are having.
So they said that we have to take your permission to ask them to send the PDF. So that's
Okay.
why I'm
Okay.
asking.
Okay, okay. I will tell them. Okay.
Okay.
It's not a
Thank
problem. Okay, but what is the important thing is you try with yourself first. Okay, so solution key, generating solution key is not a big deal. Okay, the problem is if you are able to approach in the right way, and not that we are not restricting our approach. That you can get your own intuition, and you try to prove it, but try to have some mathematical proof. It's not like it's obviously it's naturally, okay, it's clearly, it's not, these things will not sometimes work, okay, for explaining the mathematical things.
Sir, can you please show that proof that Cauchy is convergent? I
Yeah,
have one
proof
doubt
is
in that.
okay. Proof is readily available in this reference book.
Means I didn't understand after that we selected choose from x1, x2, x3 up to.
Where?
Well,
Means like in the book?
no, here in the slide which you.
No, I have shown that convergent sequence is Cauchy, not the converse. I have not shown that sequence is
Yeah, yeah,
convergent.
yeah.
I have
In
shown
that
that,
only I have doubt. Can you please open up that slide?
yes, Cauchy. Every Cauchy sequence is bounded and
No, the right side of this.
yeah, this proof.
After this.
Means okay, up to this is fine. Means
Yeah, yeah.
okay,
This is.
convergent, and you are able to where this happens.
Yes, sir.
Okay. Then we have used the means add and
No, sir,
subtract the
not this
limit
slide. After
value.
this.
Okay. Yeah. Okay. So limit value. We use the fact that means the triangle
After this
inequality.
too.
Okay. And then this is epsilon plus epsilon for all, because see this result,
Sir,
this
after this slide.
after this slide.
Yes.
Okay. Means every Cauchy sequence is bounded.
Yes. That you
Oh.
have chosen from some set of x1, x2, x3.
Okay. This one.
Yes, yes. So
Okay.
how do we know that xn is always less than m? We don't know that xn is monotone, means if it's increasing or decreasing. How can we say that xn is always less than m?
See, we are here, we have created an artificial M to look at. Okay. Now, see, the very first step, if you first line, if you focus it, that is mod xn is less than the certain this right hand side. This is bounded by the right hand side. If you take any n greater than equals to h epsilon naught. Okay. Okay, so that you can call this some number. Let's say this is some m1. Okay. Now, but there are some members or finitely many members below h epsilon naught stays. Okay, so h epsilon naught minus 1 stays, epsilon naught minus 2, and so on till x1. So how do we bound them? So suppose you have taken, so these are finitely many. So for the finitely many, oh sorry, this is going to be maximum here.
Yeah.
Okay, this is maximum here, so that I forwarded here.
Yeah. Okay.
Now it's fine.
Yeah, yeah.